Hello again. This geometry video is about conditional statements. This is section 2 of chapter 2. And let's get into it. A conditional statement is an if-then statement. I'm sure we've used them. If it rains, then I walk. This is just an example. Now what we call it rains is the hypothesis. That's our if part. So the hypothesis we would connect to the word if. So if it rains is the hypothesis. The then part is the conclusion. So in this example, the conclusion is I walk. A truth value simply means, is this conditional statement true or false? Now some new symbols, some new notations. This lowercase p represents our hypothesis. This lowercase q represents a conclusion, and this arrow indicates that we do have an if-then statement. So P represents the hypothesis, Q represents the conclusion, and together with the arrow, that represents a conditional statement, an if-then statement. And our truth value is either T or F, true or false. Now when determining whether a conditional statement is true or false, if we can arrange a Venn diagram to represent our conditional statement, this helps tremendously. So let's take a look at a Venn diagram. We'll use some number sets for a few conditionals here. So real numbers include fractions, 1/2, 2/3, and they also include negative fractions like -4/5, right? I'm just listing some real numbers here. Real numbers could also be numbers like whole numbers, or 0, or negative numbers. And we could also have integers. Now we're getting more specific. Fractions do not qualify, but the positive and negative whole numbers, -4, -3, etc. 0 is an integer, and then positive whole numbers 1, 2, 5, 7, any of these are integers, but natural numbers are only the positive counting numbers, 1, 2, 3, 4, 5, 6, and so on. So if we know about these number sets and we have them in a Venn diagram, which if you're not familiar with Venn diagrams, it means that a natural number, the further inside we go to the Venn diagram, this will also be part of an integer, and likewise a natural number will be a real number. But not every real number is an integer, right? 1/2 is not an integer. Not every real number is a natural number. -4/5 is not a natural number. So the more inside we are, the more specific we get. So let's do some truth values. If a number is natural, then it is real. So we're starting inside and we're working outside. When we do that, we will get a true response. And you could sit here all day trying to find a counterexample to disprove this, but we just won't find one. Now let's move on to the second one. If a number is an integer, then it is natural. So in this case, if we're starting at an integer and saying that any integer will be natural, I can immediately find a counterexample. -3 would be my counterexample, which makes this statement false. Anytime we can find a counterexample to disprove a conditional statement, we've proven it false. So next one, if a number is real, then it is an integer. So now we're starting from outside and going in, and right away I can find a counterexample 1/2. So my counterexample for this conditional statement would be 1/2, and therefore my conclusion is this is a false conditional statement. Last one, if a number is an integer, then it is real. We're starting inside and working out. That will be true. So here's our conclusion. If a conditional statement goes from more specific to less specific, working inside of a Venn diagram, working your way out, then it will be a true conditional statement. Now for some more vocabulary from this section. The word negation means not. And so let's look at an example here. That we were given, M is the midpoint of segment AC. The negation of this statement would be M is not the midpoint of AC. Pretty simple. New symbols. This is our hypothesis. This symbol right here means not the hypothesis. Or the hypothesis is P, this is not P. So anytime we see this symbol, this is implying a negation of a statement. Next vocabulary word is converse. In the context of conditional statements, a converse means to switch the hypothesis and conclusion. Pretty simple. So here's an example. If we have this conditional, if it is Tuesday, then I eat pizza, the converse would be, if I eat pizza, then it is Tuesday. Here are the new symbols. This is our given conditional, hypothesis and conclusion. If then, we switch. Now we say, if the conclusion, then the hypothesis. Later on we will try to determine whether these are both true. And if they are both true, then we have a special new kind of conditional statement. That'll be later in chapter 2. This vocabulary word, inverse, is to negate the hypothesis and conclusion. So here's an example. If a triangle is acute, then its circumcenter is in its interior. We'll learn about those things later, but the inverse of this conditional is this conditional. If a triangle is not acute, then its circumcenter is not in its interior. So an inverse of a conditional is to negate both the hypothesis and conclusion. And here would be the notation. If P, then Q, the notation for an inverse is, if not P, then not Q. And our last vocabulary for this section is the contrapositive statement. Now this is a kind of conditional statement where we exchange and negate the hypothesis and conclusion. So here's an example. If a shape is a square, then it has 4 right angles. The contrapositive would be, if a shape does not have 4 right angles, then it is not a square. And here are the new notations. This is our given conditional, if P then Q, hypothesis conclusion. We switch and we negate. So this is read, if not Q, then not P.